3A Scientific Measurements. 3.1 Measuring in the Creation Mandate. The Mars Science Laboratory mission and Curiosity are all about measuring. The rover itself is a marvel of design and measurements. What size must a gear on Curiosity's robotic arm be to make it move properly? How hot must its laser be in order to vaporize a rock? But these are just a few of the questions of space science. Here on Earth, what's the average volume of air in a person's fully inflated lungs? What's the distance between carbon atoms in the diamond of an engagement ring? How low is the air pressure inside a tornado? These and similar scientific questions can be answered only by measuring, gaining useful knowledge about God's creation. The purpose, true science, demands that we make measurements of every facet of nature. Measured information allows us to use what we know more effectively, to return glory to God, and to help our fellow human beings. 3.2 Measurement the Basics. What exactly is a measurement anyway? When you measure something, you compare some aspect of the thing that you are measuring to an appropriate measuring standard. Such a standard is usually an instrument with a graduated scale. We need to define some keywords in this description so that we understand fully what a measurement is. Once you have identified the dimension you want to measure, you must compare it against an appropriate standard. A standard. That is a known quantity of a dimension that everyone agrees to use for. Comparison when measuring. Later in this chapter, you will learn about the important standards scientists refer to when they make measurements. An instrument is any man-made device a scientist uses that includes the standard for measuring. Human senses aren't reliable and can't produce numerical measurements. We can't even sense some phenomena, such as gamma radiation or bacteria. So an instrument extends, refines, or substitutes for human senses. Mechanical instruments include a graduated scale and electronic. Ones display a numerical value. The spacing of the markings on scale shows the units of the dimension that the mechanical instrument measures, while a digital display usually shows the abbreviation for the unit. A unit is the name and the size of a portion of a dimension that has a value of 1. The dimension standard defines the size of the unit. 3.3 Measured data. Data is information collected from scientific observations. For scientific data to be useful, scientists must be able to collect and report data clearly. For this reason, scientists report observations using either numerical measurements, quantitative data, or precise word descriptions, qualitative data. Observers are far less likely to misinterpret, due to bias, instrument-measured quantitative data compared to qualitative data. Thus, it is the preferred kind of scientific data. Scientists collect qualitative data when they can only describe an observation, not measure it. Measured data usually has 2 parts, a number and a unit. The unit accomplishes 3 things. It signals that the preceding number is a measurement. It indicates the kind of dimension, and it identifies the size of the dimensional unit. 3.4 The metric system. As international shipping expanded during the 17th and 18th centuries, trading in foreign ports became more difficult. Weights of grain, lengths of cloth, and volumes of oil all had different units in different countries. Many merchants limited their trades to ports that used the same units. At the same time, scientists all over Europe were communicating more and more as they shared scientific theories. Although the language of science was standardized, Latin, the units of measurements were not. Increasingly, the European scientific community was finding it difficult to communicate important discoveries so that fellow scientists could understand. Many scientists realized that they needed to settle on a standard set of measures. But which one? Every nation wanted to make its own set of units, the basis for the new common measuring system. International bickering about this matter went on for decades. Finally, in 1799, France established a decimal metric system. The decimal designation means that the units of each dimension and any other units based on these are related by powers of 10. The French metric system first contained 2 standards, the meter, m, for measuring length, and the kilogram, kg, for measuring the quantity of matter. The French originally defined the meter as 1/10,000,000th of the distance from the Earth's North Pole to the equator along the line of longitude that passed through Paris. They manufactured a bar made of a corrosion-proof metal alloy to show the length of 1 meter. Between two carefully scribed marks, the French defined a kilogram as the mass of 1 cubic decimeter of water. They made the standard kilogram in the form of a cylinder of the same alloy as the meter. Bar. Scientists all over Europe eventually adopted the system because its standards came from physical quantities and it was easy to use. New standard units had to be included in the metric system as the existing fields of science progressed and new branches appeared. One of the roles of normal science is refining the standards by which it operates. See the Science and Truth facet on page 10. So, scientists developed more exact ways of defining the existing unit standards in ways that did not rely on physical objects. For example, in 1983, scientists agreed to define the meter as exactly the length of the path that light travels in a vacuum during 1299,792,458 second. The second itself is also a metric unit, exactly defined as the time required for a specified number of oscillations of a certain kind of light wave. Physicists required these demanding standards because of the increase in accuracy and precision of scientific measurement. However, the kilogram is still based on a physical object, because scientists have not yet been able to develop a standard of mass based on other exactly defined units. The standard kilogram resides in the International Bureau of Weights and Measures, BIPM, at Sèvres, France, under carefully controlled environmental conditions. There are 6 copies of the standard kilogram stored with the original. National institutes around the world hold about 100 other copies. Even with a workable metric system, many countries continue to use local traditional systems for trade and government work well into the 20th century. In 1960, the countries of the world finally agreed to adopt a single global metric system. An international conference renamed the system the Système International d'Unité in French. The more common abbreviation SI comes from this name. The French metric system began in 1799 with 2 base units. Today, the SI has 7. A base unit is one defined by a set of measurable conditions that can be recreated in any properly equipped laboratory anywhere in the world, true of all but the kilogram. Appendix B lists the SI base units and the conditions that define each dimensional standard. Table 3.1 lists the 7 SI base units, along with their dimensions and unit symbols. SI base units and derived units. SI base units have their own unit symbols and can't be expressed as combinations of any other SI units. The SI also includes many other units scientists require for their work that are combinations of the SI base units. These other SI units are called derived units. In this course, you will become familiar with many SI derived units, such as the liter, L, which is a UNT of volume, the Newton, N, which is a unit of force, and the joule, J, which is a unit of energy and work. Metric prefixes. The metric base units alone are useful for a very limited range of measurements. How would you like to measure the thickness of aluminum foil in meters, or the volume of an ocean in cubic meters? Since the SI is a decimal system, we can define units larger or smaller than a base unit by multiplying the base by a power of 10. See Math Help box below. You can know the size of a metric unit by its unit prefix. A prefix indicates the exponential factor needed to give the size unit you want. For example, the prefix kilo tells you that the metric base unit is multiplied by the factor 1,000, or 10 cubed. A kilometer in kilomates is 1,000 meters, m. You can see by this that the relation 1m carriers 1 or 1,000 kilometers is also true. The prefix milli stands for 1/1,000, or 10⁻³ power, times the base unit. A milliliter, ml, is 1/1000 of a liter. Similarly, it takes 1,000 mSi to equal 1 L. Each prefix has its own abbreviated symbol that combines with the symbol of the base unit. See Table 3-2 below. We can adapt the base unit for any metric measurement. For example, we measure distances between cities in kilometers, km or 10 cubed meter, while we measure the thickness of aluminum foil in millimeters, m or 10 minus 3 power m, or micrometers, or 10 minus 6 power meter. Yet nearly every country has an organization that standardizes the rules for using the SI prefixes, since these are established by international agreement. In the United States, the National Institute of Standards and Technology, NIST, enforces these rules for scientific work. 3.5 Unit conversions. Metric conversions. A teacher gave 3 groups of students the assignment of measuring the length of a table in their classroom. Each group received a different ruler. One ruler was graduated in whole meters, the second in just centimeters, and the third in millimeters. The teacher recorded their results on the board. Group A, 2 meters. Group B, 200 centimeters. Group C, 2,000 millimeters. Do their measurements agree? They measured the same quantity, but came up with different numbers. We can check the results by converting all the measurements into the same unit, say the meter, by using a conversion factor. A conversion factor is any factor that multiplies a measurement to convert its unit to a different but equivalent unit. A conversion factor has the following properties. It is a fraction. Its overall value is equal to 1, since same-sized quantities are in both the numerator and denominator. The value in the numerator has the unit you are converting to. The value in the denominator has the unit you are converting from. After multiplying the original measurement with the factor and canceling like units, the result is the same quantity, but is a new number with the desired unit. Let's see how a conversion factor works when converting between metric units. Group A's measurement is already in meters, 2 meter. You can convert Group B's measurement, 200 centimeters, cm, to meters, by knowing that there are 100 centimeter and 1 millimeter. See Table 3-2. If 100 centimeters is the same as 1 millimeter, then 200 centimeters must equal 2 meters. However, most unit conversions aren't this simple. The following steps show how to find the conversion factor and then make the unit conversion. The slash marks show cancellation that occurs during division. Recall that like factors cancel in the numerator and denominator of a fraction. If there are like units in both numerator and denominator, they cancel. Just like numbers, remember that multiplying by a value equal to 1 does not change the size of the original measurement. The goal here is simply to change the measurement into a value with different units. Check the measurements made by Group C is 2,000 millimeters. The same as 2 minutes. We can find the answer by starting with the relationship 1,000 nem ser mir mer 1 mem. You may occasionally need to convert between 2 units whose direct relationship you do not know. For example, how many seconds are in a week? Simply use more than one conversion factor in a series of steps to convert from the given unit to the desired unit. You probably do not know the number of seconds in a week, WK, but you do know the number of days, D, in a week, the number of hours, H, in a day, the number of minutes, min, in an hour, and the number of seconds, S, in a minute. The conversion from weeks to seconds requires 4 factors. Unit conversions between different systems. Conversion between different units within the SI is nearly always a matter of finding the right power of 10 to relate the 2 units. But how do you convert measurements between SI units and English units, such as those used in the United States? For example, while vacationing in the Canadian Rockies, you see a road sign that says Banff, Alberta, 35 kilometers. How far is that in miles? Unit conversion between different measurement systems follows the same process as above. However, conversion factors from English to metric units are almost never equal to exactly 1. Because of this, the unit equations involve one rounded number and are only approximately equal. To convert the distance to Banff to miles, use the following relationship. If you use the relationship 1 nanometer about 1.609 kilometers, which is a better approximation, the calculated distance is about 21.8 meters for these. Kinds of conversions refer to Appendix D to find the appropriate. Unit relationships.